Okay, so we're going to we're going to talk about functions and function notation. Okay, so in our study here in our class, we're going to deal a lot with functions. So it's important to kind of start by defining them, right? Now, I want you guys, as you work through this, and there's some of these terms you probably have heard before throughout your math career, but I just want you to pay special attention to the definitions and make sure you are clear and understand what we're talking about when we say a function as opposed to a relation, right? Now, I'm sure you've seen lots of different functions throughout, and some of them are functions, some of them are what we call a relation, right? So let's start by kind of starting our more basic definition before we jump into functions, and we're going to define what a relation is, right? So in terms of mathematically, we're going to say we define a relation right, is a set of ordered pairs. Okay. Now, the set of ordered pairs consists of two parts, right? First of all, it's ordered, right? So what comes first and what comes second is very important, and it's a pair, so there's two of them. All right. Now, the first part, the domain, right? That's what we define as our first component. Sometimes called the input, right? Sometimes called the independent variable. Or what we refer to as our xval. Okay. Now, the second component, referred to as the range. Right, so this is our second component. Sometimes called the output. Sometimes called the dependent variable. And sometimes known as y. And all of these we kind of use interchangeably when we're talking about our first and second component, right, or our domain and range. Now, a set of ordered pairs, right, so what we mean by that is a set when we're dealing with math, right, usually is denoted by we have these curly braces here to denote that we are referring to a set, right? An ordered pair can have the form of something like this, right? Let's say 1, 2, 3, 4, 5, 6, 7, 8, and 9, 10. Right? So looking at this, we see this set, right, has 5 ordered pairs, right? Each of these, in the parentheses, right, signifies one ordered pair. All right, so that's 1 element, 2 elements, 3 elements, 4 elements, 5 elements. All right, so here we list it out, which we can do in a set. We can list out all its elements. Right. In later sections, we'll see different ways to write a set, but for now here, just kind of listing out all its values is a proper notation here. Right, now based on our definitions of a relation here, what is the domain? Right, so let's say, all right, so looking at this, what is domain? Right, the domain, right, if we look at our definition, is the first component. So domain is going to consist of 1, 3, 5, 7, and 9. Right, so again, there are 5 elements here from each of our ordered pairs. It's the first component. All right, now the range, that's the second component. So that would be all of 2, 4, 6, 8, and 10. Okay, and that would be our range. Okay. Now, you may be thinking, well, I know what a function is and a relation, right? Maybe, and they don't always come in this form, right? And they don't, right? Sometimes we don't think of an equation as a set of ordered pairs, but the following the following here, these equations, sorry about the mess here, right? Now, all of these are relations. Some of them are functions, right? So how do I know which one is a function and what makes a function different from a relation, right? And again, we might not think of these as ordered pairs, right? But that's exactly what they are, right? If you're trying to think of a graph, right? A graph is just representing an infinite number of ordered pairs, right? That's what the graph of a relation is, right? So now what differentiates this a relation from a function, right? So now let's define what a function is, right? So when we refer to a function, so a function is a relation in which each possible input value leads to exactly one output value. And sometimes reference, we say that the output is a function of the input, right? We give the function some input value, it does some calculations, and out we get the output value. All right, now one thing to notice here is that a function is just a specific type of relation, right? Notice the relation, the definition of a relation is a very broad term, right? It's just a set of ordered pairs. Now a function gives it more structure, right? It tells me, right, it's a set of ordered pairs, but it also has this other property that it needs to satisfy, right? It also needs to have each possible input value leads to exactly one output value, right? So focus on that word, right? Exactly one output value. Right now, if you think of this abstractly as a relation where, let's say, a relation where this is the input and then this is the output, almost like maps, right? We're going to map the input onto the output, right? And let's say the input consists of some values, just to keep it very general. Let's call them A, B, C, D. Those represent some real numbers, right? And the outputs, let's say, let's call them J, K, L, M. All right. And then here, let's say that A is the input and it maps to J, B maps to K, C maps to L, and D maps to M. All right. And then we want to ask ourselves, is this a function? Is the above relation a function? All right. And we could see that and we could say, all right, well, let's reference our definition here. And we say, all right, function is a relation, which we do have here, right? Just a set of ordered pairs. An ordered pair here would be AJ, BK, etc. Right? Each possible input value leads to exactly one output value. You have A to J, B to K. Yes, I would say that that does satisfy that definition. So we would say yes, it does. Okay. All right. Okay, so let's look at another example here. All right, so let's say for another relation, we have, let's call it x, y, z. We have our input and our output. And then here, let's just say x. Let's say j and k. All right, and let's say here, the relation that we have here. Okay. All right, so this is our relation, right? Now again, it is a relation, right? A relation is simply a set of ordered pairs, and that's what we have here, right? We have xj, xk, yk, and zk, right? Now let's ask ourselves the same question, right? Is the above relation a function? Okay. All right, so now let's look at our definition here. Right, the definition says each possible input value leads to exactly one output value. Well, I do have something that contradicts that definition, right? If I look at our first input, x, that leads to two output values. It leads to j and it leads to k. So here we have two ordered pairs, xj from our relation here and xk. This violates the definition, right? We have two output values. So two output values. So that is in contradiction to what we stated a function is. So that is enough to say no. Okay, let's take a look at one more example here. So here, let's say we have the following relation. Here we have our input, and here we have our output. Okay, and let's say again, let's do x, y, z, and let's say here we had just one output, j. And let's say here we had the relation was this. And we want to ask ourselves the same question, right? Is the above relation a function? Okay, so let's reference our definition again, right? Now, a function is a relation in which each possible input value leads to exactly one output value. So let's see if that's true here. We have one input leads to one output. This one input, y, leads to one output. This one input, z, leads to one output. In this case, all the outputs happen to be j. But that does not violate the definition. Right? It doesn't say that those outputs have to be unique. Right? So in this case, if we look at all the ordered pairs, right? And we just say, all right, well, looking at this, that doesn't violate our definition. It doesn't say anything. Remember, the definition of a function doesn't state anything about what that output needs to be, whether it has to be unique or not unique. All right. So looking at this does satisfy this definition. Okay. Now later we'll see as we kind of will add more kind of restrictions or more conditions that need to be met, right, for our function, and that would signify special types of functions. right? Where we'll look into what's a one-to-one function, all right? Things like that, all right? As well as other ways to determine whether a relation is in fact a function using a graph, all right? How do I know? By looking at a graph, all right? Now, moving forward, right? I think we've all been used to using, like, let's say y equals 3x plus b, or let's keep it numbers, 3x plus 7. Right? When we're dealing with functions, we're going to use this notation interchangeably. We'll probably use this notation here, which is read as f of x. Right? It's telling me that I have a function of the variable x, right? Or in this case, x is our independent variable. Okay, so we'll get comfortable that these are kind of, we use interchangeably, right? Y and the f of x. Okay, as the standard, we use y as our dependent variable. So if we want to show that something is a function, we'll usually solve for y to see if we can find one such function that is y equals to something. Okay, so what we learned so far here is that in our math we have this big old set of relations, right? If we think of almost like a Venn diagram here, right? This big old set represents all relations. All right. Now, within the set of relations here, there is a little subset, right? Not all relations, as we've seen, satisfy that definition, but inside there we have functions. All right. So there are a specific type of relation, right, that satisfy the one that each input leads to exactly one output. Okay. So moving forward, we'll look at other ways to determine whether a relation is a function, and then how to evaluate, using this notation, how do we evaluate the function as well. All right, thank you.